In the previous video, we defined the term electron affinity, and we looked at electron affinities for lithium, beryllium, and boron. So we talked about their respective values and what they meant in terms of structure of the neutral atom and of the ion that formed. In this video, we're going to talk about trends for electron affinity. And in terms of a group trend, some textbooks will tell you there's a modest group trend. Some textbooks will tell you there is no group trend. At any rate, there is more of a clear trend going across a period, and so that's the one that we're going to look at instead. And so if we analyze some of these numbers, we'll start with boron here. So boron gives off 27 kilojoules per mole of energy when you add an electron to the neutral atom. When you move on to carbon here, more energy is released, right? 122 kilojoules per mole. And if I look at oxygen, 141 is given off, so an increase. And finally, fluorine, 328 is given off, so even more energy is given off. And remember, the more energy it's given off, the more of an attraction the nucleus has for the electron, so therefore the more affinity the atom has for the electron. So electron affinity increases. And that bothers students sometimes because they think about this negative sign. But remember, that negative sign just means energy is given off. So just think about the magnitude if the negative sign is confusing to you, right? So fluorine would give off 328 kilojoules per mole, so that would be the most. So once again, as you go across a period, in general, there's an increase in electron affinity. And so there are several exceptions to that general trend, and we talked about a few in the previous video, right? We talked about why beryllium doesn't have an affinity for an electron, and we also talked about the reason that this number and this number don't quite fit up with our trend. And so first let's talk about why that general trend is true. So as you go across a period, right, you're increasing in terms of nuclear charge, right? So boron has 5 protons in the nucleus, carbon has 6 protons in the nucleus. So that's an increase in the number of protons, and there's not a whole lot of difference in terms of electron shielding, and so your effective nuclear charge increases as you go across a period. And so the effective nuclear charge is the charge that the electron that you're adding would feel, and so therefore, since your effective nuclear charge is increasing, the electron that you're adding to the neutral atom would feel more of an attractive force, and so therefore the atom has an increased affinity for that electron. And so that's the reason for the general trend that we see here, right? So the reason for these numbers for boron, for carbon, for oxygen, and for fluorine, right? Increased number of protons in the nucleus. All right, let's think about one of the exceptions to that general trend, right? We can see nitrogen has an electron affinity of 0, which means it's going to take energy to add an electron to the neutral nitrogen atom. And let's think about that in terms of electron configurations. So for nitrogen's electron configuration would be 1s2, 2s2, and 2p3. So if you want to put that into orbital notation, right, we'd have the 1s orbital here, 2s orbital, and then we have 3p orbitals in the second energy level. So let's fill in those electrons. So we have, let's go ahead and change colors here. We have 2 electrons in the 1s orbital, so those would be our 2 electrons. 2 electrons in the 2s orbital, and then when we get to the p orbitals, right, we have 3 p electrons. So we're going to put 1 electron in this orbital, in this p orbital, 1 in this one, and then finally 1 in this one. So that's the neutral atom. If we wanted to add an electron to nitrogen, right, so we can see that we have a half-filled p subshell here. So if we're going to add an electron, we're going to add an electron to one of these p orbitals, and let's say we add the electron to this one over here. Right, so the electron that we added to magenta, right, has to occupy the same space as the electron in green. So when we spin pair those electrons there, that increases the amount of electron-electron repulsion, right, because those 2 electrons are occupying the same orbital there. And so that, of course, that extra repulsion means that this is not energetically favorable. So if we were to add an electron to nitrogen, right, we'd have a negative charge now, and this would no longer be 2p3, this would be 2p4. And again, that extra electron-electron repulsion is the reason that you usually see given in textbooks for the fact that nitrogen does not have an affinity for an electron. So let's talk about neon next, right? So neon's over here, and neon also does not have an affinity for an electron, so an electron affinity of 0 here. So let's think about why that is the case. right? So the number of protons in neon is 10, right? Its atomic number is 10, so there are 10 protons in the nucleus, so 10 positive charges in the nucleus like that. And there are 10 electrons, right? So if we think about where those electrons are, right, there are 2 electrons in the inner shell. So here's my very crude representation of the inner shell there with 2 electrons, and then 8 electrons in this shell here. So in the second energy level, right, 8 electrons in this shell like that. And so if you were to think about adding an electron to neon, let's go ahead and write neon's electron configuration here. So neon would be 1s2, 2s2, 2p6. And so let's just talk about where I'm getting those numbers from my diagram here, right? So the 2 electrons in the inner shell would be these 2 electrons, and the 8 in this outer shell here would be the 2 and the 6, right? So 2 and 6 give us 8. And so this is our electron configuration for neon, and just a little picture about what it would look like. If you wanted to add an electron to neon, right, your second energy level is full, so you have to move to the third energy level. So you have to open up a new shell. So if I wanted to add an electron to neon, it would have to go into a new energy level. So the electron would have to go into the 3s orbital. So 3s1, this would make this negative charge now, and we know that it's a new energy level. So we can talk about the electron we're adding being on average further away from the nucleus. Right, so that would be the picture, and we know that this positive 10 is going to try to attract this electron that we added. However, you have all of these inner shell electrons here shielding this other electron, and so because of these electrons in here, right, repelling it and screening the outer electron from that positive 10 charge, the atom has no affinity for that electron in magenta that we are adding, and so that's the reason for the value that you see here for the electron affinity of neon. So it doesn't have an affinity for an electron, and so this anion would be very unstable. And so the idea is, of course, that neon lacks the sufficient nuclear charge, right? It doesn't have enough positive charge in the nucleus to attract the electron in magenta that we would be adding to form the anion here. And so that's the idea. And so hopefully this just gives you a little bit more insight into the general trend for electron affinity and also some of the exceptions.